true. There's always that one day when everything's just going really smooth, and then like that one day it just like makes you get
There's false lines?
Yeah, that's what I was saying.
Okay. So I want 3 different ways, 3 different graphs where our first derivative is positive. What does that mean about f?
It's increasing.
It's increasing. So somebody come draw me a graph where our function is increasing. Okay, draw one. Take one of those axes and draw where it's increasing. Okay, pretty simple. Somebody draw a different one.
Increasing the entire domain, or is it?
Yep, increasing. It can't be a line.
Oh, yeah, I get it.
Yeah,
Every 2.99%.
Okay.
That's only horizontal.
Anybody else?
Horizontal.
Yeah, yeah.
I like that.
Nice.
Okay.
Nice, okay.
Okay. Carter, I like your creativity. I'm going to take a piece of yours, like this right here. Right? Okay, so that's what I want you to focus on. This graph, this piece, and this. Okay? Those are all increasing, those are all different. Right? Okay. This one is increasing fast or slow? Fast. This one is increasing, but it's slowing down, right? And this one is increasing constantly. This is what we call concavity. Concavity is the direction of the curvature. Okay? We have either concave up or concave down. Okay? So those 3 pictures that we drew, they all were increasing, but they all looked different because of the concavity. Okay? So this one is concave up, and this one is concave down. Concave up is like a cup, it will hold water. Concave down, everything will spill out. So, let's think about this. If, stand up before we go to the next slide. Don't want to freak you out. F prime tells us how the y values are changing. Are we increasing or are we decreasing? Okay? The second derivative is going to tell us how the slopes are changing. Okay? Let's talk about what this means. This curve is what? Concave down. Okay, I'm going to draw a bunch of different tangent lines, and you're going to tell me what's happening with their slopes. Okay, what's true about this slope? It's pretty steep, right? And then let's look at, I'm going to use it. What's happening with the numeric value of each of these slopes? Our slopes are getting smaller and smaller and smaller. Okay? When we are concave down, our slopes are, what's a good word to describe getting smaller and smaller? Oh, decreasing.
Shrinking.
decreasing, that's kind of an important word, isn't it? You have heard that one before. Okay? Here we have concave up. Okay? From left to right, I'm going to draw these slopes. What is happening with the numeric value of these slopes? Okay? When we are concave up, our slopes are increasing. And when we think of increasing and decreasing, we think of the
First derivative.
okay. So if we're talking about the slopes increasing and decreasing,
This is second derivative. But we're not learning about that till tomorrow.
no, actually, tomorrow is the second derivative test.
So it's like, when it's negative.
Okay. So when our second derivative is positive, we are concave up. Okay? Because that means our slopes are increasing. Okay? If the second derivative is negative, then our function is concave down because our slopes are decreasing. And if our concavity equals 0, or if our second derivative equals 0, there's no curvature in our curve. Okay? If you take the second derivative of a linear function, what is it? 0, because there's no curvature at all. We're already to slide 5.
We still got 7 more. 6 more.
7 was like the number of yesterday, so basically what we did.
Where concavity changes is where we have what we call an inflection point. What is true about the second derivative at an inflection point?
That's the exact
0 or
X is right. Y is X is
okay.
I bet Jim.
So when we look at the
Is that a graph of f of x and then
yes. So this is a graph of f of x. So here would be a relative minimum. Here would be a relative maximum. This is an inflection point. So these red points are where our first derivative is 0, or undefined. This blue point, an inflection point, is where our second derivative is 0, or undefined.
To the middle of the maximum.
It would not be the middle. It's just where concavity changes. Where concavity changes is where we have an inflection point. Possible inflection points occur when the second derivative is 0 or undefined. Okay? So it's just like when we do the first derivative, we look for where it's 0 and undefined, and then we test it, right? Now with the second derivative, we look where that is 0 and undefined, and instead of critical values, we're going to call those possible inflection points. Okay? Is every critical number a min or max? No. So it's the same kind of thing. They're going to be our possible inflection points, and we're going to test those.
So if that's where concavity changes, the slope doesn't go from positive to negative. It's like, is that when you said like?
Okay, so let's think about this. Here is where our slopes go from increasing to now our slopes are decreasing.
But would that make them negative?
The tangent slope.
Because you said it's concave down, but it's
Change from
decreasing.
concave up to concave.
When our slopes are decreasing. So this is concave down, right? Because all of these slopes get less and less in numeric value. This is concave up. All of our slopes get greater and greater in numeric value.
And,
So here is where that switches.
okay, and then, so like when we do tests, the ones to the right where it's going down, we get negative numbers for our.
So concave down, our second derivative is negative. Concave up, our second derivative is positive. Okay? Yes?
Are we going to relate related rates to this?
Not related rates, but we're going to be able to do something called optimization, and I'm not going to talk about that right now. But we are going to do some application with minimums and maximums. Okay? Like minimizing a value or maximizing a value, we're going to be able to do that. Okay? All right. So here are 3 different cases where our we might have possible inflection points. So let me just cover these up here. Okay, so here we have an inflection point. Okay, because concavity changes. Here we have an inflection point because concavity changes. Yes.
That's obviously harder, so you can't find the first derivative.
Well, the first derivative is undefined there. The second derivative will also be undefined there, but that's going to give us a possible inflection point. Inflection points can happen where our second derivative is 0 or undefined. So it can happen at this corner. So that's good that you noticed that. It's not differentiable there, which makes it a possible inflection point.
So you mean like possible? As in, is there a way for like something like this to be undefined and yet?
Yes. Okay, here are 2 graphs where we're going to get a second derivative undefined. However, the concavity doesn't change, and so it's not an inflection point. Okay, just like that example yesterday where we had a critical value, but we went increasing or we went decreasing to decreasing, right? Same kind of thing. Okay, so inflection points are going to occur when concavity changes, just like mins and max occur when decreasing and increasing change. Okay, so we're going to look at a very simple example. Are you ready? Yes.
So there's no inflection point because there's a tangent there, or there's no asymptote there.
Yes.
Then what about the third one? It says no inflection point at value x equals p.
Because we have an asymptote at p.
No,
So
the third one.
the third one?
So in other words, since they're both
Since they're both concave up, there's no change, so it's not an inflection point.
fair enough. Okay.
Okay?
But, and for the last one, it was undefined at that point, there's no inflection.
Right. Okay. Simple. Right? Okay. So if we want to look at increasing and decreasing, we look at the first derivative. What is our first derivative? Minus 3. If we want to look at concavity, we look at the second derivative. And what is the second derivative? 6x. Where is our derivative 0 or undefined? Okay, so our possible inflection, possible point of inflection would be, so I'm going to write possible point of inflection is at x equals 0. So we're going to do the same thing we did yesterday, but with the second derivative. So we're going to make our sign chart. Okay, now to keep your work organized, let's go ahead and label this as the second derivative. So you know you're looking at concavity. Okay? So to the left of 0, our second derivative will be negative. To the right of 0, our second derivative will be positive. So we are concave up where?
X equals 0.
What?
Negative infinity to 0.
Concave up?
Oh, 0 to infinity.
Okay, we are concave up from 0 to infinity because our second derivative is positive.
So unless you're guaranteed to get negative plus.
We have to test the intervals based on our zeros. Okay, we have to test all of them. Yes.
That's going to be a pair here. He rated it on for 9.
Concave up.
That's on the wrong side.
Concave now.
The handle thing's on the wrong side.
No, it's not.
That's UOP. That was pretty funny.
Where are we concave down?
Negative infinity to 0.
Okay, now it says cocaine.
We are concave down from negative infinity to 0 because
That's negative.
our second derivative is negative. Don't say it. There's no it allowed in describing. Yes. Now, what is happening at x is 0?
Inflection.
We have a point of inflection at x equals 0, negative 4. How did I get 0, negative 4?
Plug it into the original.
So it changes like that.
We need to say point of inflection.
Well, wait.
Positive or
Can you
negative.
put it into the original, like F, not F
Uh-huh.
prime? or-
Yeah, because we're describing f. We are always describing f. Okay? But we're using the second derivative to help us describe the concavity of f.
So let's just say like the sign chart like negative, then x equals 0 wouldn't be an inflection point.
That is a very good point. If our sign chart was negative, negative, we would not have a point of inflection.
Alright, so therefore would we still have, we just have concave down then?
Yes, you'd have 2 intervals of concave down. Mhm. Yes.
Why do you write possible point of inflection?
What?
Why do you write possible?
Okay, so kind of like we wrote critical values for their first derivative. They're not always minimums and maximums. So this is where our second derivative is 0 or undefined. Okay, and those are the numbers we put on our sign chart, but that doesn't guarantee we're going to have the concavity to change. Because like they were saying, what Aaron was saying is we could have something that looks like this. Okay, and this would not be a point of inflection. Okay. Yes.
Alright, so we've already figured out the, like, first go back to the original one. Is that, the F double prime, you have, on your sign chart, you have the negative and positive. So why is it still a possible point of inflection at 0, negative 4?
It's not. It's no longer possible. This is point of inflection. Yeah.
Okay.
Here it was possible.
Alright.
Okay. Somebody else has their hand up.
Brady.
I'm just holding it. Okay.
Brady.
Do this again. Okay, I want to know where this is concave up. So what is f prime? Okay, second derivative. Not everyone all at once, please.
4x squared minus 12x. So 12 squared.
Okay, so we have the second derivative. We need to look where our second derivative is 0 or undefined.
0, 1.
Okay, so because you did this, right, Jimmy? Okay, we can factor out a 12x, leaving x squared minus 1. So our possible points of inflection are 0 and 1.
PPOI.
Sure. Okay, so we're gonna make a sign chart for the second derivative. Okay. When we plug in something to the left of 0, that makes our second derivative what?
Positive.
Between 0 and 1, our second derivative would be?
Negative.
And to the right of 1.
Positive.
Okay. So this was asking, where is the function concave up? So this function f is concave up very good. How many points of inflection does this graph have? 2. We have a point of inflection here at x is 0 and a point of inflection here at x is 1. Okay, let's look at what that looks like graphically. What was our graph?
X to the 4th minus 2x cubed.
X to the 4th minus
2x cubed plus 8x plus 12.
Okay, so we're gonna have to
Then 1 right there.
oh, it's 0 and 1, huh? 2. So window. So let's go.
Why is the right side like lopsided?
So see here, boom, boom, we have a change in concavity. This wasn't a very good graph to look at.
What?
We need to do that one.
Up, window.
Chill. Chill, bro.
Boom. Oh my goodness.
Just take down. From negative to
So,
why did
there,
Like spurred on.
there, boom. So concave up, concave down, concave up.
Oh, that does not look like a concave.
We need to look at a different one.
It's a really, I can sad.
I can, well, sure, I can see it.
Do you want to go back and look at this one?
No, it's
Oh, yeah.
like 3
Is that
steps.
Do you want to look at this one?
Yeah.
Okay. What was that one? X cubed
X cubed minus 3x minus 4.
minus 3x minus 4?
Yep.
There we go.
Oh,
I was in that one.
Do you see our point of inflection?
Yeah.
Critical. Okay.
Encrypted today.
It's 0 and negative 4.
He knew gravity too.
I'm actually, this isn't actually what we're, don't write it down, don't write it down.
Don't write
Maybe reimburse.
Do it.
Is that it?
Yes.
Yes.
Okay, so we're gonna look at increasing, decreasing, and concave up, concave down.
What are we looking at now?
We're looking at everything.
I want to look at everything.
Okay.
See buttons.
So if we want to look at increasing and decreasing, we need the first derivative. What is the first derivative? 2/3 x to the, okay. Okay, so 2/3 x to the 1/3.
0 stuff.
So where is our derivative 0?
On X is zero.
I think that's just the first one.
That's the, right. The first one is going to tell us about increasing and decreasing. So what are critical values for the first derivative? 0. When I plug in things to the left of 0, we get things to the right of 0. Positive. So let's talk about what this is telling us.
Yeah,
No,
that's the bottom of the line. Okay.
that would be 0.
What if-
Right.
Well, wait.
Zero.
Yeah.
X to the 2 is the same thing as the cube root of x squared, right?
Yes.
So anything, I can put anything in there, it always comes out positive. because
Remember, we're
X squared.
talking about the derivative, though. We're plugging values into the derivative.
Why not the second derivative? Are we looking for
We're doing every.
We're going to look at increasing, decreasing, and we're going to look at concatenation. Okay? So, first derivative, we found the critical point. We tested in the first derivative. Okay, so what does this tell us? This tells us increasing from 0 to infinity, decreasing from negative infinity to 0,
And
and
minimum at 0.
would you agree 0, 0 would be the coordinate?
Yes.
Okay,
you do
great. So that's what we did yesterday. Now let's continue. Let's look at this. What's the second derivative?
Negative 2/9.
Negative 2/9 x to the negative 4/3. Do you agree with that?
Yes. Yes.
Yeah, it's not like 1/3.
So we have negative 2 over 9x to the 4/3. Okay. Where is our second derivative undefined?
0.
0, because nothing's in the numerator that can make it 0, right? So our possible point of inflection is x is 0. So we're going to make a sign chart with the second derivative. Okay. And we're going to use the second derivative to fill out the sign chart. What happens when we plug in a number to the left of 0? This is positive,
That's still negative.
right? Because x to the 4th is going to make it positive. So what happens when we plug values in from here? Okay, so let's talk about what this means. This means we are concave down from negative infinity to 0 and 0 to infinity. We cannot include 0 because the second derivative is undefined there. There's no concavity at x is 0.
So, are you still supposed to set the top and the bottom to 0 when it's
Yes.
close? Like you're supposed to find where it's undefined and 0?
Yes. Yes. So this is 0 nowhere and undefined at 0. Okay? Still the same thing, just with the second derivative. Okay? Now, do we have a point of inflection? No, we do not. Because we don't have a change in concavity. Okay? All right. Now, we are going to practice identifying all of this with a graph.
Yay.
Okay? So, this is a function. I want to know where it's increasing, decreasing, where we have minimums and maximums, where it's concave up, concave down, and where we have inflection points.
Yeah.
Okay? So, since we have a lot of things that we need to look at, let's make some sign charts. Okay? So, for our first derivative, okay? first derivative, we look at what's happening on the function.
I say the first zero would be at is about negative two-ish.
Derivative is zero.
Okay, so where is the derivative 0 or undefined?
Negative two, actually, it's like
Negative 3 first, right?
Negative 3 first.
wait, that's a zero.
Well, we have a horizontal tangent.
Is that a horizontal tangent?
Yep.
Fair enough, okay.
Here.
Negative 1 as well, the vertical tangent. Tangent is undefined at negative 1, isn't it?
Okay.
Negative one is a inflection point.
Yeah, negative 1 is not a vertical tangent. It's just an inflection point.
Okay. that's
Okay?
just like a
And
tangent.
so then we would say,
I can't, well, how do you know the difference if it's between a vertical tangent and not a vertical tangent?
Yeah, because then you take,
That looks really close.
Yeah, you know.
how could I?
I'd say just start with increasing and
Or is
decreasing.
it I equal negative two?
Where does it start increasing and where does it start decreasing?
Mhm.
So it's decreasing from negative
Okay.
infinity
So it's, okay, so where are we decreasing from?
to negative infinity to negative 3. You don't do anything to take into account the 3.
Is negative three even a horizontal tangent? Does it show?
Okay, so if we're gonna say, okay, so let's say this. If you were given a graph, they would probably say this is a horizontal tangent or not, okay? So let's just assume that that is not a horizontal tangent, that's just gonna be a point of inflection, okay? If it's a horizontal tangent, it will tell you, okay? So we are decreasing from where to where?
Negative 3, -2.
-2, and anytime else?
1 to infinity.
1 to infinity. Where are we increasing?
-2 to 1.
-2 to 1. So if we were thinking about this in sign chart form, we are negative, our derivative is negative until -2, positive until 1, and then negative again. So what's happening at -2?
Minimum.
We have a relative minimum. What's happening at x is 1? We have a relative maximum. Okay? So min, max. We'll do some shorthand here. Okay, let's talk about concavity. Where are we concave down?
-3 to -2.
So right here, -3 to -2. Where else? -1 to infinity. We'll say infinity. We'll say this. Okay? So where are we concave up?
Negative infinity to -3.
Okay, right here. Negative infinity to -3.
-2 to -1.
And then here, we're concave up. So if that's the case, then our sign chart, we'd be concave up until -3, concave down until -2. Wait, this should be a 2, shouldn't it?
Yes. Yeah.
Concave up until -1, and then concave down again. So how many inflection points do we have? 1, 2, 3, because we have 3 times where we change concavity. Okay. Now, let's talk about when we're looking at the derivative graph. Okay. Okay, so when we look at increasing and decreasing, what are we looking for on our derivative?
The slope is positive and positive.
Okay.
The slope is above 0 and below 0.
Okay, so our first derivative, we see that Our first derivative is negative until where? 1. And then we are positive until
6.
and then we are negative until 8, and then we're positive again. So our original function is increasing from 1 to 6 and 6 to 8, right? And our function is decreasing from negative infinity to 1 and 6 to 8. I said that wrong before, didn't I?
Yeah.
We're increasing from 1 to 6 and 8 to infinity because our derivative is positive. So what's happening at x is 1?
Let's see.
Because we're going from negative to positive on our derivative. What's happening at 6? And what's happening at 8? Okay. So now that we talked about that yesterday, now we have to think about what our derivative tells us about concavity. Okay, so when I said concave up means our slopes are increasing.
So every time the slope of the derivative is equal, we change concavity.
Yes. Okay, so when concave up means our slopes are increasing. Well, slope describes our derivative, correct? So where our derivative is increasing, that is where we are concave up. So where is our derivative increasing?
1 to 6.
Okay, we are increasing from here to 2. So from negative infinity until 2, our derivative is increasing, and so our second derivative is going to be positive.
Then you have, you're increasing again from 3 to 5.
Okay, well then what happens from 2 to 3, our derivative decreases. So when we take the derivative, those slopes are negative. Okay, and then from 3 to 5, we increase, so we're positive. So what's happening at x is 2? At x equals 2, we have a point of inflection. And like Zach said, that is a maximum or a minimum on this derivative graph. That's where our slopes are 0 on the derivative graph.
I thought you said that our derivative always like describes our original function. 'Cause I imagine.
Yes. Yes.
So why are you looking at the derivative graph to see the increase?
Because that's all we have. We don't know anything about the original graph. But if our derivative is increasing, that means our slopes are increasing, which means concave up. Okay. So here's your homework for tonight. What I'll do is I will have you practice the looking for concavity. Okay. And we will start off class tomorrow looking at some graphs. Actually, you know what? This is what I'll do.
So don't do the graph.
No. Do all of these, which isn't a lot. And then I want you to do number 1 and number 3 on here. Number 1 and number 3.